Good morning, my dear students. Today's class I am going to discuss about second time around echo. The, the echoes that arrive after the transmission of the next pulse is called a second time around echo, and these second times around echo very important to understand the range ambiguities. And then suppose I am transmitting the first pulse. After that I have to get the echo. But here after the transmission of the second pulse I am getting the echo. This echo is called a second time around echo. The echo that occurs after the transmission of the next pulse is called a second time around echo, and these second time around echoes leads to the range ambiguities. And the next concept is maximum unambiguous range. It is the range beyond which the targets appeared as a second time around echoes is called a maximum unambiguous range, and maximum unambiguous range is given by R unambiguous equal to C by 2fp, where fp equal to pulse repetition frequency. And the next concept is prediction of the range performance. Already we know the radar range equation. Rmax equal to PTG sigma AE by 4 pi whole square S minimum whole power 1 by 4. By observing this equation, we know that the range of the radar can be increased by increasing the transmitter power, or by increasing the gain of the antenna, or by increasing the effective area of the receiving antenna. We can increase the radar range, but this equation does not give exact range because various losses associated with the radar system, and these losses are system losses because some electronic equipment does not work well under field conditions, and second loss is meteorological conditions along propagation path, and third one is radar operator cannot work properly, and this leads to an imperfect range measurement. And the next concept is minimum detectable signal. It is the weakest signal the receiver can detect is called a minimum detectable signal, and this waveform is the receiver output waveform. In this waveform we are going to have a high amplitudes. These high amplitude indicate the targets, where A, B, C having a high amplitudes, and this indicate the targets. And for detection of the targets we are going to use one technique. In the technique we are going to establish a threshold level. If the amplitude is above the threshold, that is taken as a target, and A is above the threshold. Here A is above the threshold, it is considered as a target, and B also above the threshold, it is also taken as a target, but C is below the threshold, it is not taken as a target. This is called a missed detection. Even though target is there, that is missed. That's why this type of phenomena is called a missed detection. So if the threshold level is too high, you can miss the targets. If the threshold level is set too low, the noise also above the threshold, the noise also considered as a target, that is called a false alarm. That means exact proper threshold level is very important to eliminate false alarm and misdetection. Suppose if the threshold level is too high, the targets are missed, that is called a misdetection. If the threshold level is too low, the noise also exceeds the threshold and the noise also appeared as a targets. This is called a false alarm. So that the proper choosing of a proper threshold voltage is very important to reduce false alarm and misdetection. It is in the hands of the radar operator, so that the utilization of the experienced radar operator will improve the target detection. And next concept is receiver noise. The noise is a unwanted signal which interferes with the wanted signal. The noise may be originated within the receiver itself, or it may enters through the receiving antenna. Even though the receiver is a very perfect receiver, we have a small noise. That noise is called a thermal noise. The thermal noise is due to random motion of the electrons in the conducting parts of the receiver, and thermal noise power is given by kT into Bn. The thermal noise power is kT Bn, where k is Boltzmann constant, where Bn is noise bandwidth, where T is temperature. We're going to, if the temperature is increased, the thermal noise also be increased. And next we are going to define another parameter, the noise figure Fn. Fn equal to output noise power by the noise out of the ideal receiver. Fn equal to N0 by K T0 Bn into Ga. And for the noise figure we have another formula, Fn equal to input signal to noise ratio by output signal to noise ratio, Si by Ni by S0 by N0. From this, Si equal to KT0 Bn Fn S0 by N0. S minimum will occur when the minimum signal will occur when output signal to noise ratio is minimum. S minimum occur when output signal to noise ratio is minimum. Therefore, S minimum equal to KT0 Bn Fn S0 by N0 minimum. By substituting this S minimum in radar equation, already we know the radar equation, Rmax equal to PTG sigma AE by 4 pi whole square S minimum whole power 1 by 4. By substituting S minimum in that equation, we get the Rmax whole power 4 equal to PTG sigma AE by 4 pi whole square KT naught Bn Fn S0 by N0 minimum. This is called a modified radar equation in terms of output signal to noise ratio. Okay, this is about today's class, and thank you very much.